We got a talk here on weaponizing hypervisors by Ali and Dan. And we have a little tradition here at DEF CON for those that are new to speaking at DEF CON. And does anybody know what that is? Yeah.
Thank you.
So this is called Shoot the Noob. And those of you who can cheer them on as we do our shot here for the first-time speakers. All right. Good luck, fellas.
Should we start?
Yeah, go ahead.
Hey guys, thank you for coming. Really excited to be here. It's our first time, as you saw. I am Ali Islam. I'm the co-founder and CEO of Numen. I've been in the cybersecurity industry from last 13 plus years, and for a long time I was working for a company called FireEye. It's another cybersecurity company. So that's Dan, you wanna?
Hey guys, my name is Dan Regalado. I'm so excited to be here because it's the first time in DEF CON, so glad and blessed. Y quiero agradecer a mi esposa, a mis hermanos, a los amigos, a esa banda mexicana que está aquí, señores. DEF CON speaks Spanish.
Cool. Okay, let's get started. So here's a quick overview of how we organize our talk. So we're going to introduce some of the basic concepts. These concepts are really important and kind of a foundation upon which we build our later detection cases and other policies. Apart from that, then we're going to explain the whole embedded environment, the journey, setting up the board and the environment that we play in. And then we're going to talk about the very important VMI on ARM. I'll explain shortly what VMI is. And finally, we'll discuss about different attacks, use cases, and some of the recommendations. Okay. So why is hypervisor so important and relevant? As you can see, all of the major players, automotive-grade Linux, Renesas, Denso, and Alibaba NXP, Perom Robotics, there are many, Green Hill, Intel, they all have now the hypervisor in their architecture. And the traditional use case for hypervisor is basically the efficient utilization of the resources and probably the isolation use case. However, not many people have explored hypervisor for security in terms of how you can use hypervisor to build a really good security system. Isolation is there, but not the VMI that we're going to talk about. Okay, so the beauty of hypervisor is that it exposes an interface which is called, the introspection interface. It's also called virtual machine introspection. What it does, or it allows you to do is, you can monitor the whole system from the outside. That's really powerful, and we haven't seen many people using it, especially on the ARM. So we were very, very excited to start on it, and it was a long, very hard journey because there's not much out there. There are like few projects or papers out there. So traditionally, the antivirus, we all know that it has a lot of issues. It sucks. But mainly, when any advanced malware comes into the system, the first thing it does is basically check if there is an agent inside or if somehow it's being monitored. And if you're sitting outside of the operating system, you solve that very important problem automatically. So basically, you have that sophisticated invisibility. Apart from that, not having anything inside the operating system also helps with the different certifications because you're not messing up with the device functionality. Imagine you're securing a car infotainment, and then suddenly there's a bug in your software which kind of messes up everything, right? So you don't want that. Okay, so let's get started on the VMI. what is VMI, or what kind of interface hypervisor exposed? Basically, what you have is raw memory. And you take the raw memory and you use some of the OS specific knowledge to actually make sense out of it. For example, you should really know like where kernel is storing what, and then you kind of like build your logic around it to really make sense out of it. For example, if you take the raw memory and you know where the Linux task list is stored in the memory, you can go to those offsets and then you can start decoding, and finally, as you can see here, you can decode this task list and traverse this task list from the raw memory. To give you an example, for example, if you have to read a kernel symbol value from the raw memory, it looks like a simple thing if you are inside the operating system. However, from a VMI, it's a very complex process. So what will happen is, first of all, once you say, hey, I want to read the value of this virtual address, first of all, VMI. By the way, we are using libVMI. We highly recommend. It's an open source project. It kind of provides the basic functionality that you need, and on top of that, we build our own functionality. Some of the basic functionality might be like the I'll explain you shortly, like once this is done, for example, the caching and some of those capabilities. So we really recommend using libVMI. So what will happen, let's say if you have to read the value, you'll get the virtual address. libVMI will first go and check with the system map to see where the virtual address is, and then take that and then map it to the page directory. The page directory will be added to some of the bytes from the virtual address to map to the page table, and finally to the actual physical location in the memory. And then it will come back and give that value back to the VMI application. So that's the general flow of how you can get the value out. Also, here you can see that once you go through this process, you're not going to do that again for this particular virtual address. So that's where, again, libVMI comes in. It has a very efficient caching mechanism. You can do on your own also, but in case you want to avoid some of that work, you can just simply use the libVMI. Okay, another very important concept that is critical to what we're going to show you is single stepping. Because we're going to show you eventually how you can get the system calls out by staying outside of the operating system through VMI and from the raw memory. So I'm sure you have all used debuggers and single stepping in your own use cases, including reversing. However, there are other single stepping and breakpoint mechanisms that I want to quickly touch on. The hardware breakpoints is basically are mainly used for code that sits in the ROM. So basically, when the code is not in the RAM, you cannot override the breakpoint instruction. So what you do is you have these special registers provided by ARM and Intel. For example, on Intel, it's D0 to D3. And you store those memory location values in those registers. And then when program counter comes to that particular memory location or that instruction, it just halts the execution, and then you can analyze the whole system. Another is the software breakpoints, is the most common one. CPU assisted that we use in debuggers. For example, you will set the trap flag in the eFlags register, and then you'll let the CPU do the work. Once the breakpoint hits, the CPU automatically do the single stepping. But what really is single stepping? When we say step, what happens in the back end? So in the back end, what happens is there is a special instruction, for example, called int1. When the breakpoint hits, you do the whole analysis. However, in the back end, that instruction, the CPU makes sure that it also executes the original instruction, and then move on, and then move on. So that's very important. Now the third one is the software breakpoints with no CPU assistance. So we're going to use that in our implementation, and there are reasons for that that I will explain you once we are done with the basic concepts. But just keep that the concept, the single stepping concept in your mind. Apart from that, in our implementation, as I said, right, you're playing with the live raw memory. So you really need to know how the kernel internals and how the kernel is, organizing the memory and how everything is working inside. So you need to have that basic knowledge. So we all know that from quite some time we now have the paging, the virtual addressing since 286, where the real addressing mode ended. And then this is a typical two-level paging. We also call it SLAT, second level address translation, or and it is implemented using the extending page table and the virtualization extensions that the newer architectures provide nowadays. So to quickly follow the flow, like I was saying, for example, if you are going to read a value, this is how it looks like. So basically, you take the first 10 bytes, add it to the CR3. CR3 is a special register which stores the base of the page directory. And you add that 10 bytes to the CR3, and then it takes you to the base of the page table entry. And where then you again pick the next 10 bytes, and then you add them to get to the right page table. And finally, you add the 12 bytes, which are the offset, into a specific memory page from which then you fetch the value. Okay, this is another view of just what I just explained. So 2 levels of translation. First, from virtual machine to the VM physical, VM virtual to VM physical address, and then from VM physical to machine physical. So basically, you have this hardware on running right on top of the. By the way, we're talking about the bare metal, the Type 1 hypervisor, right? So you have this hardware, the hypervisor is sitting right on top of it. And then, there are like different domains or the VMs. So the second level of translation is handled by a table called extended page tables, and there is a pointer EPT. For example, Xen hypervisor stores that per VM, and it is used to do the translation. EPT, there is something very interesting about EPT. So what EPT, as you guys can see, what EPT is doing is it is eventually giving you the value from the memory, right? It points to the eventual physical location where the value is. And the newer virtualization extensions, for example, Intel and ARM, they have a way where you can store multiple EPT pointers per VM. Now that is very powerful because one, you can, for each page table, there are permissions, right? So you can assign different permissions to it. And that way, for example, if you assign permission execute to one page and then read write to another page, you can play with those permissions. And I'm going to show you later in our talk some of the use cases. But for now, I think it's very critical to what we're going to do, or what we have implemented in our implementation. The second interesting fact about EPT is, like, you can, as I said, you can store more EPT pointers. So apart from partition, what you can do is you can actually point a EPT to a different memory location. Now what that means is, basically, for example, if you are you have to translate one virtual address, right? You can play with that last level of translation, and then at one time you are giving one value, at the other time you're giving another value. So basically, you are using the same code, you are creating two different behaviors, which is very powerful, and there are many use cases for it. And you can see the code snippet in the Xen where it stores and the permissions also. Yeah, that's the one I was talking about. Like, for example, the second EPT is actually pointing to another memory location. And I'll also talk to some of the implementation details. It looks easy, but it's not that easy. So, for example, you have to create all of the pages in the memory yourself. Well, Xen hypervisor, for example, do have APIs. So, but they're not very well documented. So you have to play with them. and you create, for example, increased reservation is one that you can use to create pages. So once you create the pages, you have to maintain all the mappings, but Zen provides the functionality to switch between different pointers. And another very important aspect of this is like, this switching between different EPTs, or you can call them the memory views, because essentially what you're doing is you're creating different views of the memory. So you can present one view to one user and other view to other user, and by user can be a malware also. The best part is that the VM exit is a very expensive operation. What by VM exit means is like when you're running your domain on top of hypervisor, and suddenly the control has to be transferred to the hypervisor. What that means is hypervisor has to store all of the virtual CPUs inside that domain, the context of all those virtual CPUs, and then get out and give the control to the hypervisor. But switching between these EPTs, there is no VM exit. So it's very fast, and I will explain later like why performance is very critical to anything you're doing, especially building a detection system using VMI.
So, okay guys, so once we understand the basics, we started playing with an environment, right? We need to have a board to play with this whole implementation. In our case, we didn't have a specific board. So we went to LinkedIn, we just Google Xilinx, Xilinx FPGA creators. And it turns out that this guy has a pretty cool board, which is MPSOC CCU 102. The problem was that that board is $2,500, just a starter kit. So we talked to those guys. We tell them, hey, you know what? We have this project in mind. And kudos to Xilinx. They just ship the board to our house. And then we started playing with the whole environment. So this is the board. It's just a standard inputs and outputs. So we have an SD card to root the rootfs. We have Ethernet, UART, is JTAG. And we have quad-core A53s that are the ARM CPUs, dual-core R5F. So this is the board that is very expensive, but don't worry, what we are presenting can be used in any other board. So the first thing that we were learning, guys, because when I am a reverser, exploit-related guy, this kind of board, I never played with it. It was very challenging because we are running Zen hypervisor on it, and there is no implementation on this board with the VMI introspection on it. So it was kind of hard for us because there is no support. So we learned that there is a Peta Linux project, which basically helps you to deploy the whole information into the board so that you can boot it up. It's pretty cool. The only problem is that it works with specific images. So we have our own Zen hypervisor custom deployment. So it was a problem for us. That's the first thing. Second thing is Peta Linux is for Xilinx, right? What if tomorrow we want to deploy the same environment in Renesas, NXP, others? So we don't want to just tie to Xilinx-related stuff. So then we went to Yocto. Many of you guys know Yocto very well. Well, in my case, it was like, I don't have an idea. It turns out pretty cool. The only problem was that the rootfs at the end was VCBox related. That was a pain in the ass for us because once we have everything up and running, we really need Python libraries to run our machine learning stuff. And it was a pain to just compile a single library, like TensorFlow, for example, machine learning. So it was pretty cool, pretty easy to run. But at the end of the day, a VCBox, rootfs, it was a pain for us. So we end up choosing dbootstrap. dbootstrap allows you to have a rootfs, in this case ARM64, Debian-based flavor. So you have apt-get, you can download all the libraries. So it was the way for us to go, very recommended instead of the previous one. Now, in the dev environment, guys, so you don't want to push everything on the board, right? Because the board is like the production environment. So you really want to have a test environment. So in our case, we pick chroot, which is a wrapper for chroot. It's pretty cool because we have our Ubuntu Intel x64 environment, as you can see in the picture in the bottom. So with this Intel-based environment via chroot, you can using QEMU, you can root into the environment. You can do your testing, install libraries, connect to internet, everything like you were in the board. But once you test everything, then you can jump into the board. It's pretty convenient for us. Now, let's boot the board, right? So what do we need to boot the board? Xilinx has a specific debugger, which is called Xilinx System Debugger Client. What it basically does, it reads a TCL file. That TCL file, just you guys to have an idea, what basically is doing is going to boot 4 different files. The PNUFW, which is just to set up the clock and the platform management on the board. Then the first stage bootloader, which is going to initialize U-boot. Then U-boot, which is going to allow us to boot the hypervisor, in this case Zen hypervisor, then the Linux kernel, and finally the rootfs, and the BL31, which is ARM trusted firmware. We didn't play with these components. We just use them with the versions of Xilinx. Important to mention that if you combine versions, it will never boot the board. So we have a lot of pain trying to play with different versions, and it was not booting. So once you reach this initial stage of JTAG, you get into the U-boot prompt, and now let's boot the board, right? So the first thing is, you know, the data device tree blob. That's where all the configuration from the board is located. So the first thing is the root location, right? Where is your root FS that you want to boot on? In our case, it's an SD card partition, as you can see there. Then the second thing is we have our Zen hypervisor. We just convert it into U-boot format with that command line, and then you start booting up the system. You know, this is the typical U-boot commands. So the first thing is U-boot the Zen DTV, which is the device tree blob in a specific location. Then you boot the Linux kernel. That Linux kernel, you see the 80,000 address. That must be exactly the same address that you have in the DTV. Otherwise, when it is booting up, it's not going to find the Linux kernel address, and therefore it's not going to boot. And then you load the Zen hypervisor, and finally you run the bootm, which is basically telling you, okay, so boot the board in the address, you know, 140,000, which is the Zen hypervisor. Then the hyphen in the middle is telling that you need to grab the rootfs direct path from the DTV, and finally you have the Zen DTV. With this, we can boot it to the board. These specific steps, guys, for us, it took us many days and months because it was a lot of issues booting the Zen hypervisor. Another important point here, guys, is that those addresses that you see there loading, if you don't have enough space between them, they are going to overlap, and then your board is going to crash. So suddenly we were just, you know, booting up, it was crashing, and turns out that you need to have enough space for every single memory address, but there is no validation on it. So you need to make sure that wherever the Zen hypervisor is loaded in memory, the Linux kernel, that has enough space so that you don't overlap and you don't, you don't get a kernel panic or Zen hypervisor problem.
Okay, so let's get the damn syscalls out, huh? Basically, I don't know. I mean, it was kind of almost became a dream for us to see this ARM syscalls on the screen because we've been going back and forth. We tried different things. We always got stuck because as I said, it's not very well documented, and there are few research papers out there. So we were like just trying different things, playing with the memory, and finally, we figured out, or we did our own implementation. So as you guys remember, I was mentioning about single stepping, and why single stepping is very important, and why we're going to use the known CPU assisted single stepping. The reason is since we were using the Zen hypervisor, and Zen hypervisor does not support single stepping on ARM. So we have to figure out our own way of doing what normally a CPU does. And we found a very interesting paper online. We talked to that guy also, Sergey from Germany. And then we reviewed some other techniques online, and we finally decided to use this technique. It's a very fascinating one. So remember, EPT helps you create different views of the memory, right? And so the first step is basically you create two views of the memory. By views, I mean you just take the whole memory, take all the pages, you create the copy of those pages, and then you have these 2 copies in your memory for those pages. And then since Zen hypervisor provides this support to have multiple EPTs, so you point one EPT, let's just call one view default view and the other the single stepping view. So you have 2 EPTs now. One is the default view. Default view is the one where you're gonna run by default when the system starts. That is the view where the control will be and the execution will happen. And then you have another view in the memory waiting if you want to switch to that one. So we have these 2 views, and I'm talking. Remember, I'm talking in context of the syscalls. So the goal is to start monitoring the ARM syscalls or the operating system calls on an ARM platform, right? So think of it like, okay, you want to monitor a particular system call. The code is in the memory somewhere, so you find the location of that that API in the memory. So at the first instruction you put 1 breakpoint, and on ARM is sorry. So on ARM, the breakpoint is this D40003. It's also called SMC. It's a special instruction. On Intel, it's int3. So you can use the same for Intel also. But you don't have to use this one for Intel, just to mention that, because Zen actually supports single stepping on Intel, so you can just use that one. So on the first instruction, you put 1 breakpoint in the default view. And then on the second instruction, you put another breakpoint, but in the single stepping view. Now what will happen? In the control is in the default view, and you just once the first breakpoint hits, what you do is you do your analysis. You want to get the syscall. You note down all the parameters, what process called that syscall, whatever analysis you want to do, right? And then you switch the view. You switch the view, and the control will go to the instruction 1 in the second view. The instruction 1 will get executed, and then the second breakpoint will hit. When the second breakpoint hits, again you get the control, you switch back to the default view, and then the second instruction gets executed. So basically that's how you single step on ARM if you're using the Zen hypervisor, and not many hypervisors support ARM, so Zen is probably your best choice, or unless you want to build your own hypervisor from scratch, that is an option too. So this techniques is very fascinating, and as I was saying, this is one of the applications of the views that the underlying architecture provides through the virtualization extensions. So that's how we single step on ARM in our implementation. So let's take a look overall. How do you now, as a detection or as a monitoring system using VMI, how do you monitor from the outside, right? So using all the concept that we have so far shared, right? So what you will do is, first of all, you will put a hook on every function or every API in the memory that you want to really analyze, or for example, you might want to always analyze sleep, because malware use sleep a lot. So the first step is to put that breakpoint, go to that memory location and put that instruction. And in combination, you have to register an event. Now, a good hypervisor always provides an event mechanism, right? So you wanna monitor something, it provides you an event mechanism. And Zen does the same. So you register your event, and then you also register your callback. So that's the second most important, because with the callback function that you're going to register, what it does is you're telling the hypervisor, hey, anytime my breakpoint hit, you give me the control and execute this function. So in this function, you're going to do everything. For example, you're going to extract, once the breakpoint hits, you're going to extract the parameter values of the function, the function name, process name, or whatever you want to do, you do in this function. The single stepping functionality that I showed you in the previous slide, you will also do in this function. So that's the second most important step. The third step is obviously, you need to single step. Remember, so if you don't single step, what will happen? The breakpoint will hit, you don't single step, the control will stay there, it will continue to execute the same instruction, the system will get into a very unstable state, and imagine you're protecting a car infotainment, and then you will crash the system. So it's very important to make sure you properly single step. And finally, once you're done monitoring, make sure you remove all your hooks from the memory, and you do a very clean exit. So that's how you basically do the syscall monitoring through VMI. And on ARM especially, it was challenging because as I mentioned, there was no single stepping and there was no documentation. So it took us some time, but finally we're very happy that we achieved this. So let me now show you how it looks like, our moment of happiness when you first saw this. So I hope it. Okay, so how do I show it?
Click escape in the.
Okay.
Escape the presentation. Yeah. Yeah. Okay.
And then yeah. So this is our Xilinx board. We have our introspection framework. We call it Numen introspection framework. And yeah, this is how the syscall looks like. The process name and everything. Now see, we are typing, and then you see all the syscalls being logged on the upper right. And then now I type top, and then you can see the process name top being tracked. This is happening, everything happening from the raw memory outside the operating system. So that's pretty cool. And now finally, we do a sleep, and then you're going to see the sleep being shown, and not only shown because we have other components. It's also being monitored as highlighted here. So not only we get these syscalls out, we also send it to our machine learning model to monitor it. So that was our. It took us quite some time to achieve that one, and yeah, that was the.
Okay, guys, so let's get to the fun part, because after this whole effort, as you can see, now we know the basics. We know how to use BMI to introspect into the machine learning, into the machine. Now we are able to have the board, everything, right? Now let's see what we can do from attacks perspective and detection with these components in the board, right? So the first approach is a typical malware coming into a car, into a medical device, right? How can we tackle that problem from BMI? So if you have been working on antivirus companies or sandbox-related companies, is the typical way to do it is very common. But keep in mind here, guys, we are out of the box. We don't have an agent inside, and that's a totally different beast. So let's see the first example. In this example, we have a malware running. So what we do in this specific scenario is we're going to use machine learning in order to detect attacks. So what we do is we get, let's say, the infotainment from the car, and we profile it. Get all the processes running. We feed it into our autoencoder, which is neural network based approach. And what it's going to do is it's going to learn how a healthy system looks like, all the processes, all the different syscalls being executed. So once it learns that, when it is running a process in the infotainment, it's going to grab that profile, which is in the left side, the actual profile. That is going to be fed into the autoencoder. And then the autoencoder is going to create a new profile based on his learning experience. Once it's generated, if the similarity between the reconstructed profile and the actual profile that was running in the device has really low error, which means is very similar, is when we know we are dealing with a benign process. But what happens when we have a malicious process? So the same process happens. We have this malicious process. We profile it. We create the actual profile, feed it into the autoencoder. The autoencoder is going to create his own reconstruction of the profile, and it's going to realize that the sequence and the syscalls being used is totally off. The error level is really, really high, and that way is easy for us via machine learning to detect that there is an anomaly inside the device. That's a pretty simple step one. Second approach, guys, let's say that we have an exploit going on, right? In the left side, you can see an application running and the list of all the syscalls going on there. So you are going to see always the way it executes. But what happens if suddenly that application is compromised? So if you see in the right side, at the end in the red in the red square, you will see that comparing the two applications, the benign one without being exploited is going to exit the program. But when you look at the second one, it's going to call execb. Why execb? Obviously because it's gaining a shell. So in this case, we don't really need machine learning to realize that the flow has been affected, right? We call it sequence-based. People call it control flow. Same SHIT. So at the end of the day, you just need to measure the sequence-based and realize if there is any alteration. And in this case, one exits properly, and the second one called execb, so it's easy to detect. Now let's talk about the delay. If you guys are familiar with antivirus and sandboxes, right? One of the techniques of the APTs, for example, is to delay execution so that it executes and then it's going to wait for execution so that an antivirus needs to take a decision in milliseconds to know if it is malicious or not, right? It cannot be scanning the process all the time. So by delaying the execution, those engines are going to give up and they are going to stop monitoring it, and that's a way to bypass it. So that scenario is a pain always in the enterprise with antivirus. In our case, it's the same issue, but how we tackle it comparing with them. So in our case, for example, we have this pretty simple delay in ARM, and it's just a simple loop that is going to, delay execution for 8 seconds, 8 minutes, and then after that, it's going to trigger the shell. If you remember the previous slide, in that one, we have all the execution. At the end, we have the execb to be called. In this case, what happened is that the execb is never going to be called, and therefore, we're not going to see any anomaly. So that's a pretty challenge that people have. So what the people does, for example, in the sandboxes, they hook all these sleep or nano sleep or those syscalls, and once they see this syscall triggering, let's say that there is a sleep for 5 minutes, they will change at runtime the 5 minutes to 0 so that they force the malware to execute, right? That's one technique, but that is a cat and mouse game because today is sleep, tomorrow is nano sleep, and there's going to be multiple techniques all the time. So you need to keep updating these techniques so that anytime there is a new way to bypass it, you need to update it. In this case, for example, we don't even use an sleep. We don't use a syscall. So in this case, it's just a code that's going to delay execution. So you cannot rely on hooking syscall. So this is a challenge for everyone. In our case, we tackle it in a different way. One way is you don't want to monitor these executions all the time, right? We were talking about we are in a car. We don't want to delay execution. Can you imagine the GPS just slowing down or any application in the car? So we need to decide quickly. But if this application is running and it's sleeping, we cannot wait forever. So we have a way to tag the process so that when the process starts running, suddenly goes to sleep, we stop executing, and then we monitor it in a way that we can know when the malware wakes up. There is a way to do it via profile-based approach that Ali is going to explain in a second. But from BMI perspective, same challenge, but we don't want to follow the syscall implementation in order to understand when there is a delay. In our case, we tag it, the process. You are sleeping, we sleep. We don't do any performance issue, but as soon as you wake up, we wake up. So that's a profile-based policy that we're going to explain in a second. Now, Ali was explaining us that his technique, right? The technique that he was explaining to hook into the memory. So he was telling us that, you need to put a D40003 as an MC hook, right? So that's pretty cool, but it's pretty easy to bypass. So, if I have a kernel module, I can just go to the syscall, grab the first 4 bytes, and then get the SMC there. And for me as a malware, I'm going to be able to detect right away that I'm being monitored, right? And that moment, I'm going to say, you know what, man, I have this SMB hook, I'm being monitored, so I'm not going to execute anything. I want to wipe the system, or even worse, I can override, if the memory, the page allow me, I can override that SMC hook to put it in the original state, and then I can just totally bypass the hooks in the system, and then this whole technique being shown by Ali is totally screwed because it's pretty easy to identify. So I don't know how come Ali come up with this technique, but anyways.
Okay, so let me think how we can answer Dan. So you remember the views, right? And I keep saying the views are very powerful. So here's another use case, and we'll see how we can answer Dan's question. In this case, what we are doing is, again, we are creating, two views. Actually, you don't need to create the whole memory pages. What we are essentially doing is we are assigning different permissions to different EPTs. So we have two EPTs. One is going to be the execute only. The other is going to be the read-write only. Now, what will happen? So let's say by default we are in the execute only view, right? And the malware comes and tries to read the hooks that we have placed in the memory. Since the page is execute only, there will be an exception. The control will be transferred to me, and I will see that the malware is trying to be smart. So what I will do is I will switch the view, which is the clean view, by the way. There is no hook in this view. So that's the trick. So I have this view where there's no hook. I'll switch the view. I'll let the malware read the memory pages in this view, and then its read request will be satisfied. The malware will not know, that there are any hooks or it's being monitored. So that's how. And then once that read request is done, we'll switch back to the execute view. So you saw the previous application where we created these views to do the single stepping. Now you saw another one where we use the same capability that the Intel and the ARM provides to bypass or trying malware detecting us. We bypass that.
Okay, guys, so let's see other examples. In this case, we have an anti-VMM. Hypervisors are known to be virtual machine monitors, is another name. So what we have here is, I'm a malware, right? So I want to know if I'm being monitored. If I'm being monitored, so I'm going to stop executing. So in this case, since we're switching views, as we explained, that has a cost, has a time in terms of performance. So what a malware can do, and we just do a proof of concept here, is we measure as a baseline without having the page views switching. We just measure the time. In this case, it's 38 nanoseconds, and then once we do that, we now measure the time that it takes to write into the memory. And you will see in that red color that the time is highly significant, so that you will realize that the time to write into memory is totally different to the baseline. And this is another technique that we can use to detect that we are being monitored. Just by measuring the time that it takes to write into memory, we can realize it's taking too much time than the baseline, and this is another way to find a ways to bypass, to understand that we are being monitored. Now, let's talk about process killing, guys. So when we kill a process, right, we all know how it works, right? If you want to implement it on code, you will just need to call the syscall kill, and you pass the PID and the way you want to kill it, right? -9 if you want to force it. So that's the way it works normally in a user mode scenario, and we all know. But what happened here is, what happened if we want to implement a simple killing process in VMI? Keep in mind that we don't have any agent inside. So people or other companies, what they do is they just drop an agent inside. They call kill in the user mode, and then you just kill the process. But in our case, guys, we don't have an agent inside, and we don't want to have an agent inside. We want to keep being out of the box. So how a simple kill process can be done from VMI? So we have a way to do it here. It doesn't need to be the perfect solution, but the idea here is that you guys can see the challenge when you want to just kill a simple process that is very easy to do, but from the hypervisor. So what we do is, let's say that we want to kill the process ID 300. So what we do is in the kernel, because this whole VMI, guys, is being executed in the kernel. We are not using user mode syscalls because it's too high, too consuming. It's a lot of performance issues. So we are just hooking in the kernel. So when this 300 process is running, what we are going to do from VMI is we're going to monitor all the syscalls. So when the syscalls come in from that process, what we're going to do is we're going to mess with the stack. That information that you see in the green is the full stack dumped one syscall. So what we do is, there is something that is called safe user state registers. So when you transfer from user mode to kernel mode, those registers in user mode are stored in the kernel, so that when the kernel resumes execution in user mode, those registers are used again, right? So what we do in kernel is that we get that stack content, we get those safe registers, which are not being used by the kernel, and we just nullify them. What's going to happen, guys, is that when the syscalls come back into the user mode, since those registers are totally nullified, it's going to cause an exception, and it's going to exit the process. As you can see, it's totally a different way. It's not a traditional one, but taking advantage of VMI, we are able to mess up with the stack and then force the process to kill. Important to mention that it's not easy to do, because in this example, you see the yellow box. If you mess with any kernel-related information, which is in the lower addresses, you're going to get a crash in the device. So you want to make sure that you are really overriding only the user mode register information. So we learned that from experience, and then we come up with this specific offset that is calculated dynamically, so that we always override only user mode registers. And the way it works, guys, is that every time we set to the device, hey, kill PID 300, it's going to grab all the syscalls. Every time we grab it, it's going to mess up with the stack. Sometimes in the first syscall, it gets the exception and kills it. Sometimes in the second, in the third one. So sometimes it needs to take like 5 or 7 syscalls to be called in order to be killed. But this simple example, guys, as I said, is totally different beast, as you can see. It's not easy to do it at the VMI if you want to be totally agentless. So let's see a quick example of how we kill it in the device. So here we have our system. So what we're going to do, guys, is in the upper left, we're going to run a simple malware like Mirai, which is very common one. In the upper right, we have our inspector monitoring it. Here is the Mirai. We're going to execute it. As soon as we execute it, Mirai deletes itself and spawn a BCBox process pretending to be normal, and it is in the 336 PID. So let's go back to the virtual machine that we're monitoring. We search for that process, 336, and we can see that it is there running, right? 336 is there. We click on it, and then we can see that the BCBox is showing up, right? There is BCBox. Now, let's try to kill it from VMI. So we go to our front end. We go and try to find the 336 process. We found it there. And then we click on kill button. That's going to be from VMI sending a signal to kill it. So then we go back to the VM, search for the Mirai, which is gone already. You know, it disappeared as we said. And now let's search for the 336, and you can see that it's totally killed. This is totally clean. We don't crash the system, and this way to do it, which is not the best way, it works for us, and that way we are able to kill from VMI perspective.
Okay, so just want to quickly mention that, you know, once you get hold of VMI, you understand it, it's pretty cool, and you can do a lot of other things with it. It's very powerful. So one of the things that we did in addition to detection is the policy. So not only you can do the detection with VMI, but you can also implement policies. Again, not putting anything inside the operating system and still maintain these policies. One of the examples that I want to quickly share with you is a lot of infotainments or any IoT device, for example, medical device, there are certain processes very limited which are responsible for going out to the internet. So what you can do is you can, you know, the task list that I showed you, you can continuously monitor that from the outside, and you know, since socket is a special file, you can just simply see if there is another socket being opened. That might be slow because you're actively traversing. Alternatively, what you can do is you can hook a connect or a network API, and then, you know, when events that API gets called, you will see if this process is allowed to communicate outside or not. So here's, you know, just a quick view of how it looks like in our system. Like Dan was mentioning, remediation is another topic that we are tackling aspect. Once we detect something, we need to kill. It's not easy to kill from outside. We always have that option to put an agent inside, but we don't want to do that. We want to be totally out of the box. So you want to try, I mean, the method that we showed you is not one of the, I mean, we figured that out on our own, but we have another one, you know, that we're exploring right now. So you can try different things. You can make the parameters null and try some of those things. Quickly want to share some of the recommendations with you guys for an end-to-end system. Let's say you're working with some other hypervisor, like in our case, you know, Zen is just the start. We are already working with some, you know, another hypervisor. And that's a custom one. So you really need to have good way of putting the breakpoints, efficient single-stepping mechanism, the event mechanism. Now, we didn't talk too much about event mechanism because Zen provides a really good event mechanism. But if you're working with some other hypervisor, you want to make sure, you know, you have a good event mechanism. Anything that you translate using those page tables or the page walk, you know, you want to make sure you cache those in an efficient hash tables. Multiple views is awesome, as you can see. I mean, we have few other use cases which are patent pending. We cannot talk about it. We combine the views with other techniques to really improve the performance. And in VMI monitoring system, performance is the key. And finally, the permission management. Finally, guys, we are releasing some tools for you guys to play with. You can see the Dropbox. You can go and check them out. So we have the ARM and Intel VMI monitoring tools that, you know, you can play with. We have all the files that we have used to, you know, boot up the Xilinx board. And finally, we have the one malware, ARM64-based malware that you can use to do an end-to-end scenario. So do check that out and you know, play with it. Okay, so finally, the takeaways. In today's world of advanced malware, we really need to make sure, you know, we make the hypervisor smart. Hypervisor is everywhere. So, you know, you want to make sure, you know, you make it smart, and, you know, agentless is the way to go, because we know that, you know, anytime you have an agent inside, it's a losing game. ARM syscall monitoring was a great achievement for us, but it's just the start. I mean, now there's a lot we can do. So don't just stop at the, you know, syscall monitoring. You know, think of new use cases, and, you know, especially switching between views is very powerful. So you can also think of new use cases around that. And finally, performance is the key. We have a patent pending Numen adaptive monitoring, and then we use that in our system. We cannot talk about it right now. We need another talk for that. Okay, finally, I really want to thank Saqib, Matt, Stefano, Walid. I don't know if you guys are here, but still, these guys really helped us along with our journey, and it wouldn't have been possible what we have achieved without these guys. So thank you, guys. Thank you.